Okay, so now we can get back to our ongoing program of relating material derivatives to Eulerian derivatives. And we have just done that for a material point. We are now going to do it for a material volume. So we want to know how to calculate the time derivative, the substantial derivative ddt of, let's say, B in a finite material volume. Right, so just to place our picture before us again, we have a material volume of fluid here, which is the function of time, is transforming as the fluid flow. And let's say there is everywhere defined this Eulerian field of a quantity, a scalar quantity B. And what we want to know is, how does the amount of B contained within this material volume change as the fluid moves, or as the material volume deforms and is transported by the fluid. That is, we are after calculating material derivative of the integral over the material volume, the function itself. So the limits, the volume over which we're integrating is changing as a function. And then B itself has its own local time dependence, dV. So you can see what we would like to do is rewrite this by moving the derivative into the integral. In order to do that, because then that is what we would be able to do if we could somehow represent this in an Eulerian frame or an Eulerian volume which doesn't change in time, then it would be trivial to bring this derivative into the integral, because the limits of integration wouldn't be time dependent. However, that's not the case here. So we need to find a relationship that allows us to represent this integral in terms of the integral over a volume taking the derivative into the integral. So there are various derivations of this, what is basically the Reynolds transport theorem. And the derivation we will follow will be geometric, it's intuitive, and it's also appropriate for our current level of discussion. So for this, let's go back and think about an infinitesimal change in volume. So rather than considering how the material volume transforms over finite time, since we are interested in a time derivative, we shall use the definition of a derivative, which is nothing but the difference in the quantity over a infinitesimal amount of time. Okay, so this is a material volume at some time t, and this volume, let's say, changes slightly to some nearby form. I'm exaggerating the difference, of course. So this dotted line is Vm at time t plus delta t. Alright, so the solid line is at time t, and the dashed line is the material volume at time t plus delta t. And V, of course, is defined everywhere as a function of x. So now I can, by using the definition of a time derivative, I can rewrite this as the integral over Vm, volume occupied at time t plus delta t, of B at that time plus delta t, yes, minus integral at time t. Yes, the whole thing divided by delta t in, of course, while taking the limit delta t into 0. Yes, so this is almost by, I'm just using the definition of a time derivative, and the fact that the material volume changes is represented in the fact that the integrals are changing, or the limits of integration are changing. Alright, so to make progress here, we shall now add and subtract b at t plus delta t, but integrated over the volume at time t. So you can view this as breaking up this difference into its two parts, because you see there is one part of this difference is arising from the internal time dependence, and another part is arising from the change of the limits of integration. And so we would like to split that up. So this is nothing but the limit again, delta t going to 0. Of now we have integral over Vm at delta t. I will suppress the x dependence just for simplicity, but we know it is there. And I'm going to subtract from this integral now over v, right? Plus, so I subtracted it here, I should also add it. Get t and then I have this term left over, has the same integration Vm at t, same limits of integration, so I can include it there. Yes. Of course, I have the elemental volumes everywhere. I just suppressed it for notational simplicity. All right. So now you see that this second term is easy to deal with. If I can take its limit, so the limit of this difference as delta t goes to 0 is nothing but, I can write the first term here, I can apply the limit here, write this as integral over the volume, the partial derivative of b with time, right? Because I can take this limiting action inside since the limits of integration don't depend on delta t, and it's just b at t plus delta t minus b at t as the limit delta t goes to 0, sorry, times 1 over delta t. Right, so it's this for delta, all of this. Yeah, that makes more sense. By taking the limit of this quantity, I get integral of the partial derivative of b with time. But what does the first quantity give us? Well, to understand this term, this is where we go back to our schematic. So you see the integrand itself is the same. What we're interested in is knowing how the change of the shape of the volume or the extent over the volume, how that affects the integral quantity. So you imagine now that I'm looking at b at the same time t plus delta t, but I'm asking what this change in volume, how that has affected the total amount of b contained in the volume. So what I really would like to know is, since b is the same, b at t plus delta t is the same, this difference is nothing but the integral of b of t plus delta t over the difference in the volume. Yes, and so that since that difference is infinitesimal, we can calculate it simply by calculating how the area, the elemental area, is shifted over the time delta t. So this shift of the volume is nothing but delta t times the velocity of the surface, normal to the surface. So it would be v, the velocity at the surface, plotted with the normal vector, where the unit normal points out. Let's say this is the unit normal n, and the velocity at this position might be right here, v, and so it's v dotted with n, which tells me how this surface deforms normal to itself. And so this is the sort of local distance by which the surface deforms. And so if I calculate the area integral over this surface, yes, this case is the integral over the line in 2D, but in 3D I would have to do a surface integral of this quantity, which is a distance. Yes, this would give me the volume that I've sort of displaced by moving. Right, so the first term can be written as integral over the area of the material volume at the time t. Yes, so that is now b at t plus delta t, and the area that I'm integrating, so the times to get the distance by which the area has shifted, which as we calculated was b dot n delta t dA. There's a 1 over delta t coming from here. Yes, so these delta t's cancel, and then I can then apply the limit delta t going to 0 here. The limit delta t going to 0, now that the delta t's have cancelled, is quite simple, and it's simply the area integral of v times v dot n. So what I have ultimately is the following result, that the material derivative over the moving material volume of B has two parts. One is the volume integral of the local time derivative plus a surface integral of B times V dot n. So this is the result that we are after. And it's called the Reynolds transport theorem. Yes, and you see that it tells us that the material derivative of the amount of B contained in a moving volume has one part associated with the change of B locally in the Eulerian field at every point in time, at any fixed point, as well as a component that arises from the motion of the material volume. This formula also shows that suppose at a given time, if we were to, let's say if this material volume here is at time t, the material derivative of B contained in this volume can also be interpreted by replacing at exactly this time t, if I replace this moving material volume by a fixed control volume, that is a volume that remains fixed in space and doesn't change, then in terms of that control volume I can calculate the material derivative by taking into account the local changes of B within the volume and the surface flux into that volume due to the velocity component normal to its surface. Of course, in that case, Vm would be replaced by the control volume V, but it doesn't matter because they've taken those volumes to be identical at the given time t. So this again is in keeping with that idea of writing material derivatives in terms of Eulerian frame quantities. And this Reynolds transport theorem is what is going to help us to apply principles of conservation of mass and Newton's laws of mechanics. We can go on to write this Reynolds transport theorem in a different form, which is more useful for our purposes, by applying the divergence theorem to the surface integral to write it as a volume integral, in which case would have a single integral over the volume plus the divergence of Yes. And this is the form of the Reynolds transfer theorem that we will be using in our derivations. So now that we have the Reynolds transfer theorem, we are in a position to almost immediately obtain the equation of mass conservation, and that's what we will do to end this lecture. So what does the principle of mass conservation say? Well, it basically says that mass cannot be created or destroyed, or that the mass of a material volume of fixed amount of fluid will remain the same as it moves through the fluid. That is, even if the fluid is in compressible flow, the volume of this material volume could change, but its total mass would remain the same. So what we really mean is that the substantial derivative, what we're really saying is that so a direct application of this mass conservation principle can be done in terms of the material derivative of the total mass of a moving control volume. So we say that this is equal to 0. This is a direct expression of the principle of mass conservation. But now we want to express this material derivative of the mass of a material volume in an Eulerian sense. For that we use the Reynolds transport theorem. So applying the Reynolds transport theorem, which basically means we replace E by rho, and we immediately get the statement that the integral over the volume of rho t plus divergence of rho times the velocity this must be equal to 0. Let's just confirm that. Right, so we just replace b by rho, we get the statement. Alright, so this is still an integral equation. What we are really after is a pointwise partial differential equation, and that can be obtained from this by realizing that the material volume we initially selected for integrating over to calculate the mass is completely arbitrary. Why is this important? Well, if I'm integrating this integrand over a volume and I'm saying it's 0, there are one of two possibilities. So let's say this is my volume Vm. At any given time, for all times, I know that the integral of this quantity is 0. That can mean that either everywhere in the domain this integrand is identically 0, or it could be that in about half the volume positive, in the other portion it's negative, and the quantities are such that they cancel each other out. Well, let's say for sake of argument that this is the case, but then I could have always chosen my material volume Vm to be entirely contained within a region that is positive at some time. In that case, this integral would be false. And so that is a contradiction. By this argument, it means that the only way we could have this integrand go to 0 for arbitrary material volumes at all time is if the integrand is identically 0. So because Vm is arbitrary, right, I get the following pointwise PD applicable at all across my Eulerian space. So you see, this gives us an equation in terms of the density field and the Eulerian velocity field specified on a fixed grid, on the fixed spatial coordinate system. So I can now rewrite this in a slightly different way. In fact, if I go back to the Reynolds transport theorem and use divergence again, or I apply the Reynolds transport theorem as it stands here, yes, what I could do is let's say we now fix our attention on some fixed control volume. So this doesn't change in time, and instead fluid can pass through it. As the fluid moves, I fix my attention on this fixed volume, which I'm going to call V control. I can then integrate this equation over the control volume. Rho dot T. Plus the second integral, if I use divergence theorem, will become an integral over the area of the control volume, rho V dot N. So you see, what this tells me is that the principle of mass conservation says simply that the accumulation mass plus the output minus the input equal to 0. Why is this output minus input? Well, the term will be positive if the velocity is directed along the normal, and the normal is defined as pointing outward from the domain. This is my normal vector here, this is my normal vector here. That's simply the definition of the normal. And so V dot N being positive means fluid is leaving the domain or its output. If it's negative, it's input. So this is nothing but a statement that we could have made earlier, that if we focus attention on a fixed volume, we know that the accumulation of mass is nothing equal to the input minus output. So you can see that we could have attained the same partial differential equation if we had chosen a fixed control volume, applied this principle of accumulation is equal to input minus output, written it in terms of volume and surface integrals, and then use a divergence theorem. So we could have approached it either ways, by focusing on a material volume and using Reynolds transport, by directly focusing on a control volume. However, that is because the statement of mass conservation is easy to make in this case, both for a moving material volume, as the mass never changes, or for a fixed control volume, as the change of mass is given by input minus output. However, such this sort of ease of writing the principle for a control volume doesn't transfer over to Newton's laws of mechanics. In the case of extending Newton's laws, which were originally thought of for a moving mass point to a fixed volume of fluid, the easiest way to do it is to say that the acceleration of a material volume that is moving is given by the sum of all forces acting on that material volume. It is much harder to think about how one can express this principle for a fixed control volume, where fluid is passing through this volume, and where one might have to think about input and output of momentum. And that idea is certainly not natural and doesn't follow from Newton and Euler's view of mechanics. Although once we derive the Navier-Stokes, or derive the equation, the mechanics equation for continuum, we can always do what we did just here, focus on the control volume, use divergence theorem, and then in hindsight interpret what would be, let's say, convection of momentum and fluxes of momentum, viscosity, and etc. That's typically how derivations of these equations are introduced in transport courses. But I just feel that focusing on a material volume is more natural and helps us to see more clearly that the Navier-Stokes equations is nothing but application of force is equal to mass times acceleration. But that we will take up in the next class, because we are now armed with the necessary mathematics of kinematics to describe how quantity changes as we move along with the material point, as well as how a finite amount of a quantity changes as we move with a finite volume of Oh, I nearly forgot. Before we leave, we should look at how the equation of continuity simplifies. So this was the equation of continuity, but just the mass balance equation. So how does the equation of continuity simplify for an incompressible fluid? Yes, and this is the case that we will be considering most often in this course, in fact entirely. So for an incompressible fluid, we know that rho, the density, is constant. So therefore, the equation of continuity uh, simply gives us that the divergence of V equal to 0, because d rho dt is 0 and rho can come out in the other side. So we simply have the divergence of velocity is 0 for an incompressible fluid. And this is going to be the version of the continuity equation that we will be using. Another way to understand why del dot V is 0 for such a fluid is to go back to the general equation of continuity and expand it out. So if we want to understand application, well, if we go back to the general equation and we write rho dt, plus remember it's a divergence of rho u, but the divergence of, but this is nothing but t plus rho times the divergence of the velocity. Plus what the gradient of density, just by using the chain rule of this divergence term. This must be equal to 0. But we can combine these two and you see that it's nothing but the substantial derivative. So the material derivative rho must be divergence. Take the rho bottom. As v is gone to the other side, I get a minus sign, which but this can be rewritten in the following way. If I define a specific volume, say Vs, specific volume is 1 over the density. This is nothing but the volume occupied by a unit amount of mass. That if I define this quantity, I can rewrite this version of the Navier-Stokes equations as 1 over Vs, material derivative of Vs, simply the divergence of. Where the negative sign is lost because Vs is 1 over rho. So this is also the general equation of continuity for a compressible fluid. And what it tells us is that the divergence of velocity represents the relative change of volume of a fixed amount of mass. And therefore, if the fluid is incompressible, then a fixed amount of mass can never change its volume. And therefore, it means that the divergence of velocity should be 0. So this is just a way to understand what this statement means and how it relates to the fact that the fluid should be compressible. So with that, let us conclude this lecture. And as I said, we will be back next time to take up the Navier-Stokes.